All right, so we started talking about the different kinds of neurons, and we had bipolar, unipolar. We had some that had tons of dendrites on it, some that did not. We also had sensory versus motor. So sensory said afferent going up to the brain. Motor was efferent. It was the effector. It's going to the muscle, gland, or something like that to affect or do something. And then interneurons or association neurons are the ones in between. So in between. So now we're going to talk about membrane potential, which is not that much different than what we were learning about muscle physiology. So a lot of what you learned before, you can apply those same concepts now, and then we're building on that even more. And some of the topics we'll do today we'll briefly talk about, and then we'll come back to it. So membrane potential says neurophysiology or the function of a neuron. So this is role of the membrane or ion channels. And we can have gated channels, which you guys are already familiar with, right? So we said that something had to stimulate it and it would open the gated channel and allow that ion to come through. And it was very specific, only for that ion. Nothing else could pass through but what that channel was for. So gated channels are protein pores that act as ion channels with gates that open or close. They allow very specific ions. Oh, come on. Let's try this one, that, and that. Allow specific ions to pass through the channel. And the ones we talk about most would be sodium ions, potassium ions, and, sorry, not chloride. We will talk about him a little bit, but calcium ions. Okay. And so these are different from those leak channels that we had mentioned before. Leak channels mean that nobody has to tell it whether to do it. It's just constantly, slowly leaking out. So think of like a boat with a tiny little hole in it that's constantly allowing things to leak. They're going down their concentration gradients, things that we learned in the earlier chapters. And so then the point of a gated channel would be that we allow the ion to move faster, more of it all at once, right? And then we usually have to use a pump, which takes ATP or energy, to flip it back the other way and stick it back where the high concentration side was, right? So same principles apply with this. Go away. There we go. Okay, so we have chemically gated channels, which open when the appropriate neurotransmitter binds to it. So what did we see that with skeletal muscle? Who is the appropriate neurotransmitter? ACH, acetylcholine, that I can actually say correctly today. So acetylcholine opened the gate, as an example, opened the gate for, do you guys remember who rushed into the muscle cell? For sodium, okay? Versus a voltage gated channel, which we also saw. So this opens in response to a voltage change. So where did we see voltage change with that opened a gate with the muscle? We saw it with the sarcoplasmic reticulum, and then when the voltage changed, it caused the sarcoplasmic reticulum to open the calcium gates and allow calcium out of the sarcoplasmic reticulum into the sarcoplasm, into the muscle cytoplasm, right? So we saw this with opening of SR is sarcoplasmic reticulum. So those were a voltage change. Change is a triangle, so voltage change, opened calcium gates. So you just want to make sure you understand. A chemically gated channel means a chemical, such as a neurotransmitter, is what opened the ion gate for a specific ion, versus a voltage gated channel means a voltage change occurs, and that is what opens the channel. So we're going to learn that when we hit something called threshold, it will open the gate. And in order to hit threshold, we have to change the voltage of the resting membrane potential for that neuron. So we can also have a mechanically gated channel. So these gates open in response to a physical deformation, which is typically talking about a sensory receptor. So if you guys remember, if somebody pokes you in the arm and you feel that, you've sensed that somebody has pushed into you, that's a deformation. It deformed the area in a way, so you put pressure on it. So typically that's stretch or pressure is what we're talking about on mechanically gated. Let's see, do I want to talk about anything? So in a resting or closed picture here with our purple protein in between the phospholipid bilayer here. So they're saying that this area is showing you that the gate is closed, so it's not going to allow any ions to pass through. And then if they change the voltage, so notice they have, if this is outside the cell and this is inside the cell, notice they have the negative, which we talked about before on a muscle cell where it was negative along the inner part because that's due to the negative proteins that are in there. And the outside of the cell is positive. And so if we change the voltage, and in this case they're flipping the positive on the inside and negative is on the outside, that is what caused the gate to open. And now this ion can now come into the cell. And it would be moving down its concentration gradient. High on whichever side, in this case we're saying high outside the cell, low inside the cell, so the ion can now flow into the cell. Once the voltage flips again, what do you think happens to that gated channel? It would close it. And so you're going to see that also with the neuron, that when our voltage goes back the other way, the channel closes. Thus, no more ions can go back in, and we go back to what we would call as our resting membrane potential. So, resting membrane potential, you'll see it abbreviated as RMP for resting membrane potential. Rules for maintaining resting potential. So this is all about, okay, so now we know how these ion channels may work. Could be chemical, voltage, or mechanically opened. And so resting membrane potential, so for voltage it means the measure of the amount of difference in the electrical charge on either side of the cell membrane. So do you guys remember in the very beginning we talked about potential and kinetic energy? So this is saying when it's resting, it's ready to go, it's hanging out and just waiting for the right moment. That's potential energy. So a voltage, when you're waiting for it to be able to flip, is a potential energy idea. And with current, current means movement. So anytime we're talking about movement, now what do you think we're talking about? Potential or kinetic? Kinetic energy. So it's the movement of charged particles across the cell's membrane. The charged particles are those ions, right? So we could have positively charged ions or negatively charged ions crossing the membrane through these channels. So this is kinetic energy. Resistance is the opposition to the movement of the charged particles. So this directly impacts current. And so the larger the resistance, okay, so increased resistance would cause a decreased flow or current. So current would lessen or decrease, right? So the difference in ionic composition, and let me go back for a second to resistance. So if you hear me say the term attenuates, it means it's slowing down or decreasing when we say it attenuates. So the flow or the current is decreasing when we say that. So differences in ionic composition, some of this you guys already know. Intracellular, the main cation is potassium, which we already knew, and the extracellular main cation is sodium, so we already knew that. And then it says the neuron membrane is impermeable to negative charged proteins, okay? And so do we need to say anything extra about that? Let's see. Potassium leaks out slightly faster than sodium can leak in, so it's not a lot, but it does occur. Those are those leak channels we talked about. And so because of the leak channels, they're not gated, there's no door. If positive ions are leaking out, it makes the cell slightly more negative, so that also increases the likelihood of it being negative on that inside rim, right? So it contributes to the more negative environment. Potassium is more leaky than sodium, so I just said that. So it leaves a net negative charge inside. Okay, so we know that. Sodium mostly stays outside, so it's only slightly leaky. So the positive charge due to sodium is mostly staying outside the cell. And again, these are all due to the idea of those leak channels allowing this to happen. Okay. And potassium and sodium levels at rest are maintained by, what did I say? Because we keep letting things leak out, we've got to do what to maintain that resting membrane potential? We got to use a sodium potassium pump. We need ATP to do that. So we're sticking the ions back where we want them to stay for the most part. Just so you guys know, these sodium potassium pumps, because things are leaking out 24/7, sodium potassium pumps are working 24/7 constantly all along the membrane. It's not like one pump is working for one cell. It's like tons of these proteins are all around the cell allowing this to occur. So we have these leak channels always occurring. We have pumps always returning and keeping it resting membrane potential. So how do the pumps work? So did we talk about this before with the 3? Okay, yeah, so 3 sodium are pumped out while 2 potassiums are pumped in, and it costs you how much to do this? 1 ATP. What would happen if we were out of ATP? So remember like when we talked about rigor mortis and stuff? So if we run out of ATP, we can't flip the charges back the way, we can't stick sodium back outside and potassium back inside. And if we can't do that, we can't maintain a resting membrane potential because now we're just constantly leaking out. There's nothing preventing the leaking out from happening, right? So it's still going to leak out, but now we have no way of putting it in if we don't have ATP to run the pump. So eventually, the cell can't do anything and you're just kind of stuck. Your cell won't be able to have what we'll call in a minute an action potential. It won't be able to fire. So if you don't have ATP to fix that resting membrane potential, the cell can't fire and it's just sitting there. So you want to pick up your water bottle and nothing happens, right? Yes. Okay. Say yes. All right. So let's see. So what opens and closes the various ion gates that we've been talking about again, just as a review? We could have gates on the cell body, and we can have gates on the axon. And what we're going to learn is the gates on the cell body are going to be chemically gated, and the gates on the axon we're going to learn are going to be voltage gated. Okay, so it's kind of similar to what happened with the muscle, where we had a chemically gated one on the outside of the muscle cell, which was your neuromuscular junction. And then we had a voltage gated one for the sarcoplasmic reticulum. So this is all going to occur on the outside of the cells, not inside and outside like muscle physiology, but it's all the same kind of principles. So let's look at our pretty little pictures here. Okay, so they're showing you here, you have a variety of various things. This is going to be a normal cell membrane of a neuron on this picture here. So we know that we have potassium leak channels that are constantly allowing potassium to leak out slowly, but it's happening. We've talked about how we have sodium leak channels, which is constantly letting a small amount of sodium leak into the cell. We know that we have a sodium potassium pump that's going to fix that. So it's like our bilge pump on our leaky boat to flip it the other way to prevent us from sinking. Okay, and it costs us an ATP every time we want to do that. What they did was they're sticking this thing called a voltmeter. So they're measuring the actual voltage of the cell. So they stuck that right here into the cell. So they're actually measuring the difference between inside versus outside of the cell. The inside of the cell, they're saying, is negative 70 millivolts. So that's important. Negative 70 millivolts, you're going to find, is your resting membrane potential. So that's what we want to keep our cell at, and it's the sodium potassium pumps that help keep it at that level until we want to actually make the neuron fire and actually do some sort of action. Okay. So let's see. What else do I want to say? There are more potassium leak channels than there are sodium, so that's why they put more of these blue potassium leak channels in the membrane. They only put one sodium leak channel in, which was the purple one. And then we have a couple of our sodium potassium pumps that we already talked about. They're saying the blue molecule coming in are your potassium ions. They're saying those are going out, correct? And they're leaking out. And we're saying that the sodium, which are the purple ones, are leaking in. Sodium, potassium, it's going to put 3 sodium pumped out while 2 potassium are pumped in. So that's the main thing that that picture is showing you. If we look at a diagram of a cross-section of a resting neuron, what we're seeing there is, what do you think this area, this more roundy, large area of the neuron is called? That's going to be our cell body, right? So a moment ago, did I tell you guys that we said what kind of channels are on the cell body? Chemically gated channels are on the cell body. This long part of our cell that goes that direction is called the axon, okay? The axon, we said, are going to be more of the voltage gated channels. So that's what we're seeing here. Okay, there's even one over here. And then what is this little knobby end at the end we called? The synaptic knob. So this could be a neuron that synaptic knob would have a neuromuscular junction to a skeletal muscle. It could be a synaptic knob that on the other side is another neuron. Remember when we talked about interneurons? So one neuron communicating with another neuron. So there could be another dendritic end of another neuron right there that would have his axon hillock, his axon, and then his synaptic knob or an axon terminal to a muscle or to another neuron, so on and so forth, okay? So I wanted to point that out for a second. The cell body end is the receptive end. The axon terminal or synaptic knob, the other end of the axon is going to be your effector end, right? The doer end. So transmission is only going to go one direction on this. So our receptive end, our sensory end, the side that is getting the information first, is going to be the cell body end. And it's going to send the information down along the axon to the axon terminal, okay? So that's going to be the output side. So this is input, like reception, getting the info in, and this is the output side on that end, okay? And then an important area, did we mention the axon hillock before today? So we're going to talk about that in a second. The axon hillock is kind of the wide area coming off of the cell body just before it thins out into the axon. So that's, this whole area here is an axon hillock. And of this guy here, this would be the axon hillock. And a lot of important things are going to occur right there. So we're going to talk about that area a lot. And what else do I want to tell you? 99% of all neurons are multipolar. We learned that already, right? And let's do a diagram of a cross-section of a resting membrane, resting neuron. So if you had, we're just going to draw the cell body part of it, if you will. Okay. And if it's a resting neuron, we know that it has the negative proteins, so it's more negative on the inside of the cell. We know that we have the sodium leak channels that are allowing sodium to go where? Leaking in, so we'll say leak on that one. And we also have potassium leak channels that are allowing potassium out because we know we have more potassium on the inside of the cell. We have way more sodium on our outside of the cell. And this might be a picture you could draw really quickly. And this could be for any cell, essentially. It doesn't have to be just for a neuron, right? But our neuron, we know his resting membrane potential is what? 70. Negative 70. Got to be negative. Negative 70 millivolts. Okay? So I do actually have to make you guys do some math today, but we'll come to that. So, and then what do we have to do to prevent the leak from getting out of hand? We need ATP. We need a sodium potassium ATP pump. We're going to throw how much? Who's our flip? What do? We do 3 sodium out for 2 potassium in, and it costs us an ATP to do that, correct? Bless you. All right. And so again, you have these leak channels. If we wanted to say a leak channel was a circle, you'd have all these sodium leak channels around your cell, And then let's say a triangle are all the potassium leak channels. So we have those all over the membrane. And then we'll do a star for our sodium potassium because starburst makes us think of power and ATP. So we have tons of sodium potassium pumps all over. So I want you guys just to understand this is happening all over the membrane of the cell body all the time, right? All right, that was fun, yes? Very cool. We did all of that. I talked about sodium potassium pump. All right, so now let's talk about membrane potentials that act as signals. So first we have to talk about some terminology. I think we used some of this a little bit before when I said depolarization. So that is the inside of the neuron becomes less negative. So what we're going to find is our resting membrane potential is -70. And what this might mean is if we actually have a full depolarization occur, where we flip the switch, if you will, it means we're going to go from -70 to a +30 millivolts. So how much change of millivolts is that total? Going -70 to 0, then to +30 is 100 millivolts. So that's a 100 millivolt change. So that's why it is a little important to pay attention to the negative or the positive. Okay, so our cell was at -70. We end up putting it to a +30 on the inside of the cell. It's called, we depolarize the cell, and it's a total of 100 millivolt change total. Now, repolarization means that we have to fix it, right, from what we just did. So this means the cell will now return to its resting state after it has depolarized. So repolarization only occurs after a depolarization. And so we are going from, say, we might go from -70, which was our resting membrane potential. Then maybe we depolarize, right? Now we're coming back down for repolarization, which means we have to bring it back to -70, correct? Okay. But sometimes we go a little bit more than what we anticipate, actually every time, and that's called a hyperpolarization. So hyper means more than. So we're hyperpolarizing. It means the inside of the neuron becomes more negative than the normal resting state. So what would be more negative than -70? Might be -72, -75, -100. We won't go that far, but anything more than -70 means it's gone more. So resting membrane was -70. Now we've got to get it, it'll go a little bit more than -70. How much easier do you think it would be to depolarize something? Would you only need 100 millivolts if you were at -75, let's say? You'd need 105 millivolts to overcome that, right? Okay, so that's why I want you guys to kind of pay attention to that a little bit. So we'll say hyperpolarization might be that if -70 was resting, now you've gone to -75. You've gone past resting membrane potential. You're a little more negative. It's going to be harder to depolarize again when you're in that phase. Okay, and then we have another thing called graded potentials. So this is important. So with graded potentials, these are small depolarizations, but it could also be hyperpolarization. So a graded potential doesn't mean it's always moving you in the direction to depolarize. It could bring you the opposite direction, but they're small. So this doesn't mean that you reach that threshold, is what I'm saying. So you might have many graded potentials that bring you closer or further away from threshold, but it won't, one single potential of a graded potential won't hit threshold, okay? So graded potential, small depolarizations, this is going to occur at the receptive end. Who's the receptive end of our neuron? Occurs at receptive end, which ends up being our dendritic end, right? Dendritic end. Okay, or the cell body side. The magnitude varies. So maybe it's -5. Maybe it's +10. So that can be what they're saying can vary on it, the magnitude. So depending on the intensity of the stimulus, And so if you had like a graded scale of 1 to 5, let's say 5 is like really strong, maybe one time a graded potential is closer on the one side. Another time you have a graded potential, it's more strong, it's going to be a 5. But it can vary depending on the stimulus. So for example, if you guys vary what you're doing lots of times throughout the day. So let's say if I'm expecting this to be a certain amount of weight, this water bottle, if it was more empty, it's going to be easier and quicker for me to lift it. But if I'm not anticipating it and I go to lift it up and it's super light, it might like fly over my head and I use too much strength. So the stimulus was inappropriate for what I tried to do. So same thing with your neurons. This can vary. It could be appropriate. It could be stronger or less strong, that kind of thing. Sherry also likes to use the term of like if you had a gun and you were pulling the trigger, there's a little give before you actually would fire it, right? So there's a graded amount of how far you could pull the trigger back before it would actually release. You could think of it like that. And then from gun to gun, it could vary too, right? Some guns have a hair trigger. It's super easy. So that's why you don't rest your finger on the trigger until you're ready to shoot, right? Versus a gun that might be really difficult. You'd really have to pull back and use a little more strength before it would finally fire, right? I know I was using my middle finger. I'm right-handed. I would use this finger. But anyway. Did you guys know that you can have something called trigger finger? No? People's fingers get stuck and they have to physically, it's not usually painful, but they call it trigger finger because somebody that's done something repetitive, like pulling a trigger or something, might get caught. So anyway, it has nothing to do with today. I just thought it was interesting. Moving on, let's see. So these graded potentials are also short-lived. You will have patients that have that in the future. That's why I put it out there. The impulse can't travel that far down the cell, okay? So what we're talking about is if all of this is occurring at the dendritic end, at the cell body side, it doesn't travel that much further than, say, that axon hillock. And the whole point is to get enough graded potentials to add up, okay, to cause that axon hillock to get the right amount of stimulus. We have to reach threshold at the axon hillock or it doesn't matter how many graded potentials occur. If it's not enough to reach threshold, then you won't get the stimulus. You won't get a fire. You won't get an action potential. Okay. So I'm saying all these things now. You're going to see this story build and you'll see what I'm talking about in a moment. And then the action potential is always on the axon side. So an action potential, you'll see me abbreviate as AP. This is on the axonal side, whereas graded potential was on the dendritic or soma side, cell body, right? Soma or dendritic side for graded potential. So action potential is a large depolarization, which is where we were saying we went -70 to +30, right? So a large depolarization that travels all the way down the length of the axon. Do you think it matters how long the axon is? Nope. Do you know how long one of your axons is? I'll give you a hint. Your sciatic nerve. It's about, depending on how tall you are, probably taller than me, about 1 meter long. So what we're saying is this action potential, a large depolarization that travels all the way down the length of the axon. If we happen to have an axon longer than 1 meter, it would go all the way down that 2 meter, 3 meter. We don't have any that long, but it would travel the whole way and it shouldn't attenuate. It shouldn't decrease. So think of it more like a domino effect. Once we are able to fire it, it travels all the way down the axon, no matter how long it is, okay? So this is called, so traveling all the way down is called a nerve impulse, or you'll hear me say like the nerve is firing, a nerve firing, or the nerve fired, or, you know, that kind of thing. We're all saying the same thing. And this is, remember we said it had to go from -70 to +30, so that's that 100 millivolt change typically, right? And it's an all or none event. If you don't have that change, that 100 millivolt change, you don't get a firing. That's why I said it doesn't matter how many graded potentials. If you don't reach this threshold that we're going to talk about in a second, then no firing occurs, period. If you get a firing, it's the domino effect. Once it happens, it's going to happen all the way down. It's all or nothing. That's what that means. So it's kind of like once you pull the trigger on the gun, you can't take it back. It happens. You either have enough to pull the trigger or you don't, right? And once you pull the trigger, it fires. So think of it the same way as that. So all action potentials are always 100 millivolt change. And if we get an action potential, it means we went from -70 to +30 for sure, okay? The next important term we're talking about is threshold that you heard me mention a few times. So this is intracellular set point, okay, at which the action potential will be triggered. So we're saying this usually means -55 for us. There are some cells that might be slightly variable from that, and if you're looking at old textbooks, they will mention -50, but we've updated everything with the new book changeover, so you're going to see -55. But if you're looking at an old exam, that's why it'll say -50 millivolts. So just keep that in mind. But the new, more recent research for the last 5-10 years is saying -55. So this set point is at the axon hillock. That's the important part there, okay? Axon hillock, at which an action potential will be triggered. So when we say it's at the axon hillock, we're saying this is where it's measured or where it's felt or experienced. So we go back up to that picture here. You have -70 around the whole cell, and then if you get enough voltage change to get +30 to hit our threshold, that is going to be felt right here at the axon hillock. If it doesn't have enough to reach threshold, nothing's going to happen down the axon, no firing. If you hit that threshold, you will get a firing, and then the domino effect occurs, and then that's where these voltage gated channels come into effect. So remember, it's a voltage change that affects the axon. So if we get an action potential, if we hit it at that threshold at the axon hillock, it will cause these voltage gated channels to open. That allows then, in this case, potassium to flood into the cell. If all of a sudden you have a charged ion going into your cell, it's going to change things. This literally causes the domino effect that it will open that gated channel, which makes it open the next and the next and the next and the next. And this is why it doesn't attenuate or change, and why it's always an all or nothing, and why it doesn't matter how long this axon is. This one triggers this guy to open, triggers that guy to open, triggers that guy to open, all the way down, no matter the length, okay? So going back to here. All right, so this is all or nothing, like we said. The event happens or it does not. There is no in between. If it happens, it means you got an action potential, okay? The graded potentials, there are two types that we're going to talk about, and these are dendritic events. So it also means that these are small, because we talked about on the dendritic side, they're graded potentials, so they're small. So the magnitude varies, which we already said before, and it varies with the intensity of the stimulus. They're short-lived. It doesn't travel far down. The two types we're going to talk about are the receptor potential and or the postsynaptic potential. Okay, so again, graded potentials, these are small. These are not full action potentials. If you get enough graded potentials, you can potentially then get a action potential, okay? So a receptor potential, it says if an external energy source is the stimulus, you get a receptor potential. So what we're talking about here is these are sensory, right? That makes sense if it's external. So a sensory receptor, and that means, we said a lot of times, those are mechanical deformation, where you put pressure against something, you get a stimulus on that sensory receptor, and it's going to then fire the nerve and send the signal up, hopefully towards your CNS, to tell you what it is that you experienced there. What did you think you felt? Ouch, you're squishing my finger, you're going to cut it off. Ouch, you cut my finger off. Ouch, you are just gently pressing, but I'm a little 2-year-old and I pretended it really hurt and it didn't, you know, whatever, right? So that's mechanical deformation. My younger child is always saying, ouch, and you have to figure out, is this a real ouch or I'm just saying ouch, right? If you've had kids, you probably have had one of those kiddos. The generator potential, so like a subset under this, is if the stimulus reaches threshold. So the term generator potential, automatically you should associate with the term receptor potential. So the sensory receptor is stimulated, and we have to have enough of a graded potential or enough of that mechanical deformation to initiate a threshold, which means then you have a generator potential. So always associate generator potential is sensory with receptor potential, okay? And it generates the potential. It causes it to happen if you reach threshold. The term postsynaptic potential, we're going to cover this in more detail in a moment, but a postsynaptic potential, you're going to see abbreviated as a PSP, postsynaptic potential. And it's called that because post means after, so it says occurs in the postsynaptic neuron. So when I drew that picture of one neuron and then afterwards was the next one, the first one would be a presynaptic neuron potentially. The second one, the one after, would be the postsynaptic neuron in that scenario, okay? So it's the one after. So this is what it's talking about is one neuron synapsing with another neuron. So you guys heard about a neuron synapsing with the muscle when we did muscle physiology. And in this case, since we're talking neurophysiology, we're talking about one neuron synapsing with another neuron. So neuron synapsing. C with a line means with another neuron. Okay. Action potential. So an action potential, the magnitude is always the same. These are the all or nothing event, right? So this doesn't vary like a graded potential. An action potential is magnitude is always the same. And what's our magnitude? 100 millivolts. Okay. And this is an action potential is all or none, right? It either happens or it doesn't. Okay. So back to that receptor potential, we said it was sensory. What are other things aside from touch that might be a receptor sensory type thing? Heat, so temperature, something's hot versus something cold maybe. What else? Smell, you have receptors for smell. Taste, eyesight, seeing various colors, things like that. So those are other external energy sources that we would have sensors for. So for example though, like we don't have a sensor for x-rays, but they're there, right? You get exposed to them. If you go to the dentist or chiropractor or you broke your leg and they're going to take a picture of you, it doesn't mean that they're not there just because you can't sense it. You just don't have a sensor to sense it. Or we could be like X-Men and maybe you can sense gamma rays. I don't know, right? Okay, so generation of an action potential. How do we make this action potential happen, right? So generation involves opening ion gates in the neuron membrane. Okay, that makes sense. And where do you think these gates are being opened? We said action potential occurs where? On the, yes. Say it, do it. Axon, yes. So this is occurring on the axon, okay, not the body. And the resting state means all gated channels are closed. That makes sense, right? Because we only opened it if we got a voltage change, which would open those voltage sensitive ions to come in, because we're talking about on the axon at this point, right? So it's chemically gated if we're talking about on the body side, yes? Okay, so it could be chemical or voltage gated channels are all closed when everything is resting. Both would be closed, yes? That makes sense? If a depolarization occurs, that means to become less negative, okay, because we were very negative in our cell, negative 70. We need a graded potential generated first. So that occurs on the soma side, the body side of the cell. This would travel toward the axon hillock, okay? That means that, let's say we are getting enough graded potentials. It means that we have chemically opened things up. So sodium gates open. Sodium rushes in, it causes a depolarization to begin if the threshold reaches negative 55. So anything below negative 55, if you're negative 65, negative 63, negative 58, nothing's happening, right? All or nothing, nothing happens. You didn't hit threshold. But once you hit 55, negative 55, I can't drive, 55. Okay, once you hit negative 55, now you can trigger the action potential. And when you trigger it, it will cause you to go to that 100 millivolt change total. Okay? So if the threshold is reached, negative 55, then an action potential will occur, for sure. Positive feedback and self-propagation is what's occurring here. So that just means that this is a self-propagating event. It always goes from cell body to axonal end. There's no deviation of that. And what would happen if we didn't reach negative 55? Nothing. Nothing would happen, right? Nothing happens. If you hit negative 55, then more events occur, okay? So then, let's see, sodium gates then will close when we hit positive 30 millivolts. So this is also voltage sensitive. When you hit that total of the 100 millivolt change, you hit positive 30, now the sodium gate closes. No more sodium is coming in, right? So we close the gate at positive 30. Then is going to be what's called repolarization. So this means as the sodium gates close, this now causes that positive 30 will now cause the potassium gates to open. Okay, so potassium now rushes out, which allows the cell to repolarize. Repolarization, we want it to hit negative 70, but remember what kind of happens? We're going to have a little bit of a hyperpolarization. We'll actually go maybe to negative 72 or negative 75, and then we'll level back out up at negative 70, which is our resting membrane potential. Okay, and then the sodium potassium pumps help reestablish that normal ion positions. We talked a second ago about hyperpolarization. So the reason hyperpolarization happens is because the sodium gates take a little longer to close. So they start to close, but they're not super fast, so it keeps allowing the potassium to rush out, and then it finally levels off. It closes all the way, and then sodium potassium pumps finish leveling it out, and then you're back at your resting membrane potential. So that's what this diagram down here is supposed to indicate to you. I'll try to keep some of the verbiage there for you. So your resting membrane potential is negative 70. Then you have these little blips here, these little staircases. Those are what, do you think? Those are your graded potentials. A little bit here, a little bit there. One by itself is not enough to cause an action potential, but if you get enough graded potentials to hit threshold, and what did we say threshold was? Negative 55 millivolts. So if we get to negative 55 millivolts, what's going to happen? We get a action potential for sure. So that's what this blip here is. We're hitting our action potential at the top. What happens when we hit here? We have had a 100 millivolt change, so we're now at positive 30. The positive 30 millivolts causes the sodium gates to close and the potassium gates to open. So because it closes, we're now not shooting up this way. Now potassium gate opens, which causes us to repolarize. We start to become more negative again. We hit that negative 70 resting potential, but we go a little bit below that. That's our hyperpolarization is occurring right here. And then we level out at our resting membrane potential at negative 70. And then we're ready to go again. Now potentially we could fire again at that hyperpolarization mark. We just need more than the 100 millivolts because we're below resting membrane potential. We got to go from wherever that is. If it's negative 72, we need 2 plus to get up to that 55. So what's negative 70 to negative 55 equal? 20, 15? Positive 15. So we need 15, but if we are more than negative 70, we're say negative 72, we'd need 17 to hit 55, negative 55, right? So don't forget to do that little bit of math in there. 15 is our magic number. So again, if you're looking at old exams, because they said negative 50, they are talking about a 20 millivolt change. So just keep that in mind if you're looking at old exams and you're trying to figure out why the math isn't making sense or the answer is off compared to the current information now. So if it were negative 70 to get to negative 55, you need a positive 15 millivolt change to get there. But you'd need more than that if you were still hyperpolarized, depending by how much, okay? So let's see, now what we're doing. So we said the potassium gates were slower to close, so you just want to know that they're open a little longer. That's why you get that hyperpolarization. Potassium gates are open a little longer. That's why it dips down more. All right, let's see. So positive 30 millivolts is important. Negative 55 is our threshold. That's important. Negative 70 is resting membrane potential. Those are important. So don't just try to memorize the numbers, because when you're trying to recall that info, you might get thrown off a little bit. But remember what it is that those numbers mean. And then if you get thrown for a loop on an exam question, you can figure it out. You know, if it says you're hyperpolarized, you need to add a little bit more to it. So let's see, what else do I want to talk about? So on that picture again, this area of the diagram right here, what's going on in that part right there? The sodium gates are open right there. When we hit positive 30, what happens at that moment? Sodium gates close, and thus also potassium gates open. So on this side of the curve, potassium gates are open, okay? All right. So propagation of an action potential. I'm going to scroll down a little bit. And you guys can read through the information on the chart, but it's saying everything that we just went over there. And again, it's the sodium-potassium pumps in this area at that hyperpolarization that brings you back to your resting membrane potential. That's when those guys are really working. So propagation of an action potential, self-propagating, this is positive feedback. So this causes nearby sodium axonal gates to open. Let me bring that up. So causes nearby sodium gates, which are on the axon side, axonal, okay, to open. All right, and this is like dominoes falling, right? It was all or nothing. Okay, so first sodium gate opens, means the first domino got knocked over. It then hits the second one. So the first sodium gate opens, then the second sodium gate opens, third sodium gate opens, and it doesn't matter how long it is, every single one of those are going to open down the row like a domino, ting, 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 until what? Positive 30. Till you hit positive 30. Then it'll close, ting, 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 ting. And it'll like another domino effect. Close, 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 okay? Let's see, what else do we want to say? And then also, because the sodium gates, if you reach positive 30 and sodium gates close, then what also is happening? That means the potassium gates along there are now opening. Ting, 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 ting. And then if they get to negative 70, they're going to start to close. They're just a little slower. It's not like a snapshot. It's like, I will slowly close my door. Okay, I'm closed. And then you need your sodium-potassium pumps to finish, bringing you back to negative 70, because they were like maybe negative 72 or negative 75 or something, or negative 80 even, right? Okay, so let's see. Diagram of a positive feedback action potential. So essentially you have your soma end. I didn't draw all the dendrites. Here's my axon hillock where it kind of narrows down into my axon, right? And then you'd have some sort of a synaptic knob or something at the other end, or however long your axon is. And so what was the first thing that is going to cause the graded potentials first? So our cell in general is sitting at negative 70, right? So we have negative 70 as our resting membrane potential. Sodium gates are going to open and start to come in, right? So we might have had some leaking going on. We have our sodium potassium pumps keeping us at negative 70. That's normal and stuff.
Does acetylcholine cause that? Or?
Right, because we said on the dendritic end, it could be other neurotransmitters. In this case, you could say acetylcholine causes the sodium gate to open, allowing sodium to come in. If we get enough little bits of sodium coming in, so maybe it's a negative 5 here, maybe it's a negative 2 over there, but we need enough of these graded potentials, enough little blips of this to hit what? At the axon hillock. Negative 55. Okay, that's our threshold. If we get enough of those graded potentials from sodium coming in, enough acetylcholine stimulating it, allowing a little bit of sodium in here and here and here, and then eventually you have enough that you get from negative 70 to negative 55, so a positive 15 millivolt change. Once you hit 55, all or nothing happens. If you don't hit 55, doesn't matter how much little graded potentials, they're short-lived, so they'll go away. Then maybe you get enough that come by, and finally you hit negative 55, then you get your domino effect. You hit 55, you're going to cause the action potential, self-propagating, it's going to zip down the whole thing. That voltage change now causes sodium to rush in, which would then cause the next sodium gate to open and rush in, which would cause the next sodium gate to rush in. Okay, and that will occur all the way down the axon until you hit what? Once you hit positive 30 millivolts. Once you hit positive 30 millivolts inside that axon, that's actually inside, it will cause those sodium gates to shut and thus the potassium gates to open, because positive 30 opens the potassium gates also. And then that happens like a domino effect and will zip all the way down. And only one direction. It goes from the dendritic end down the axonal end. Okay, so that direction. And then it will go all the way down, self-propagating, all or none. That's what happens. So we have a couple more terms that we have to learn, something called absolute and relative refractory periods. So what do we need to know about that? Well, I'm glad you asked. Okay, so absolute refractory period is a short period of time that the neuron is incapable of responding to another stimulus, no matter how strong it is. So it doesn't matter what you zap that neuron with voltage-wise, like a live wire, it does not matter. It cannot do anything. It does not have the ability to do it. So it doesn't matter what you do to it. It just says, and that's what absolute means. It's absolutely not going to happen. Okay, so you can remember it that way. Relative refractory period means only a stronger than normal stimulus will fire the neuron again during that time interval. So absolute refractory period is actually occurring during depolarization. And relative refractory period is occurring during repolarization. Okay. So if we look back at this picture here, I'm going to erase some of the things that I drew on it already. Maybe. There we go. All right, so if we're looking at this picture, when do you think depolarization is occurring on this picture? Depolarization, where doesn't matter what you do. If you already got an action potential, it's already happened, right? So there's nothing you could do to cause it to happen more during that time period. It's an all or nothing. It doesn't matter. You could zap it 10 more times during this period. You already have an action potential. Nothing else is going to change that. So you are in this range right here. That would be your absolute. So it doesn't matter how many times you zap something there. It's not going to change what's already happened. Okay? So that's your absolute refractory period. And when did we say, and that's when what's occurring also? That's when sodium is entering, right? Now, what is occurring when we said repolarization occurs? We said that's when those gates close and the potassium gates open. So the potassium gate side, so all of this is the repolarization part, right? All the way to the negative 70 actually, because That little chunk there is called what? Hyper, okay? So, but actually, even with the hyperpolarization part, if you have enough to overcome it, that's why this is relative. So if you want, you could say all the way to this mark here, from here to here, as long as you have enough to pop it back up to a positive 30, then you have the potential that you could do something. But it has to be pretty strong to be able to do that. So relative refractory period, only a stronger than normal stimulus will fire a neuron again during this time interval. So this is after it is fired. So actually I should say it's after in the hyperpolarization part, huh? Let's fix that. So we know that repolarization is occurring during that first interval that I drew there. That's repolarization, right? But it's after it is fired, which it did, because this was to the firing part. That's where our action potential takes us. And so after it's fired, the neuron is repolarizing during that time interval. So that still makes sense. So we can still do that. Let's see. Let's move down. So relatively, you could do it anytime during that phase. Conduction velocity of axons. So this is up to 100 meters per second. But we only have nerves that are 1 meter long, so that's why we only measure it to that. I suppose they could measure it more than that, but this is 100 meters per second. I'll say up to, okay? And if we look at the axon diameter, these are things that can affect that conduction velocity. So how fast can we get this signal, this depolarization, down the whole axon, right? So the larger, fatter, bigger diameter, the faster it would be for the conduction, for it to travel down, because there is less resistance. So larger diameter equals faster conduction due to less resistance. So if it's smaller or thinner axon, it would have more resistance and it would be a little slower then compared to a larger diameter one. We can also look at the degree of myelination. So what were the cells that did the myelination in the PNS? Schwann cells. And what did the myelination in the CNS? Oligodendrocytes, right? Okay, so it says saltatory conduction. So the term saltaire, it's not really talking about salt per se. It's talking about, comes from the root word to leap or to jump. So saltatory conduction means it's leaping across or jumping across. So these are impulse bursts from node to node. And we have a thing called nodes of Ranvier. I always thought those are cool. So if you guys were looking at your histology, you found what a node of Ranvier was, okay? So node of Ranvier, these are actually where the sodium gates are concentrated at the nodes. The reason they're not necessarily on a myelinated axon through the myelination part, remember myelin is basically just a fatty layer because it's just phospholipid bilayer that's just wrapped and wrapped and wrapped around that one little area. And one myelin sheath is not touching the next myelin sheath. There's a little gap. That gap is called the node of Ranvier. And that gap is where all of these sodium channels are located that we've been talking about that will cause the domino effect on a myelinated axon. So if it's a non-myelinated axon, they just have those sodium channels ding, 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 ding across like we just talked about. Now we're talking about we can speed this process up if it has myelin because the myelin will cause it to jump from the myelin to the myelin, and in between, so we don't lose that amount of voltage, we have those sodium gates in the nodes of Ranvier in those gaps. That's what keeps the signal strong all the way through. It doesn't like slow down or lose its amount of voltage or anything. This is what keeps it going. So nodes of Ranvier, we have sodium gates are concentrated at the nodes, which are essentially the gaps, right, between the myelin. Also, the axon membrane under the myelin, it says less attenuation of current as it travels, And there are no gates and no leak channels there because, remember, under the myelin, it's that insulating effect. So, insulating effect. So you could just think, you know, the more fat you have, the more insulated you are. You're not going to cool off or get cold or anything, right? And so then we can talk about continuous conduction. So that would be the unmyelinated axon. So comparing the saltatory conduction versus a continuous conduction. Continuous conduction was like what we were talking about a minute ago. You just have all in a row, all your sodium and potassium gates. It's the domino effect, ding, 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 and it's going to happen. But you have to open one, and then the next one triggers the next one to open, triggers the next one to open. So it's a little bit slower versus the saltatory, the leaping style. So here we have our myelin sheath. Our node of Ranvier is in between, and that's why they're showing just the sodium gates, the sodium and potassium gates right in between them. Not where the myelin is, but in between the nodes. So then you have a bunch of sodium gates there, and you'll have a bunch of sodium and potassium gates there, okay? So what it's saying is, this is trying to show you, like, this is, if the first gate opens, then the second gate opens, then the third gate opens. They're showing you, see how, like, little, you're not leaping, you're just kind of taking baby steps, right? Little tiny steps for the next gate, for the next domino, for the next domino. In the next picture, they're saying, okay, if this one fires, it jumps way over to the next node. And then those sodium gates go dink, dink, dink in the little spot in that gap, and then it will jump to the next node. Okay? So the difference is I'm telling the internet people, I'm going to take baby steps first, and then I'm going to leap across the stage here. So it's going to take me a little while to get to the end of my axon, yes? Versus, I should go in the same direction, shouldn't I? Because we only go in one direction. Versus, and I have short little legs, but I still get across the stage faster if I'm leaping and jumping those gaps, right? Essentially. Does that make sense? I almost died, and luckily I did not. I was not expecting the chair to be right there. All right, so that's all that picture is trying to get you to see is the difference between a continuous conduction versus the saltatory conduction, because you guys know you have some nerves that are unmyelinated and you have some nerves that are myelinated. That's just the difference between the two and how they will function. So some of you guys may have heard of MS before, or multiple sclerosis. This is a demyelinating disease of the CNS. So who are the CNS myelin cells? Oligodendrocytes. So this is something that affects the oligodendrocytes. Those are the guys that are getting deteriorated, and it's literally unwrapping the myelin sheath. If you take away the myelin, what do you think happens to the conduction? It slows it down. The signal may not get to where it needs to go. You will notice the person might be uncoordinated muscularly, so they will also be weaker, okay? And other things deteriorate as well, but this is the main part behind MS. And so, and they also may not get the proper sensory, so the information coming in may not be the proper signals. Things are getting interrupted, so that's what's happening though, but it's, so it's a disease that affects the oligodendrocytes. It slows down transmission, more uncoordinated events. The motor neurons would become uncoordinated. The sensory neurons, you might get abnormal sensory information. It is a deteriorating disease, so it progressively deteriorates. It gets worse and worse. That's all we'll talk about on this one for now, but now you guys know multiple sclerosis, the main thing that's happening and why. The synapse. So the synapse is the functional connection of one neuron to another neuron or effector, because where did you guys see a synapse with muscle cells? It was the neuromuscular junction, right? So with the neuromuscular junction, synapse was between the neuron and a skeletal muscle. That was the effector. Now we're looking at a synapse between one neuron and the next neuron. So it's the axonal terminal of the presynaptic neuron coming into contact with the dendritic side of the postsynaptic neuron is where our synapse is occurring, okay, between those two. So the terminology presynaptic means before the synaptic cleft or synapse, so the pre-cell, the first cell, and postsynaptic cell is the second cell, the one after, so just after the synaptic cleft. And again, that could either be a neuron, muscle, or gland, depending on what you're talking about. And then the synapse is the gap in between, right? So mainly we're going to look at number 3, which are the chemical synapses. But just briefly, we'll talk about electrical synapse. These are uncommon. That's why we don't talk a whole lot about them. Uncommon or rare and found only in the brain. And it says it's similar to the gap junction in other tissues. So you guys remember a gap junction was a way for one cell to communicate with another one, and the gap junction was like a bridge between the two. So literally, information from the cytoplasm of one cell could communicate with the cytoplasm of the other cell, right? That's why these are uncommon. We don't see a whole lot of this. It's in the brain only. And we saw those gap junctions with smooth muscle in the muscle section. So we're talking about CNS when we're talking about in the brain. We can have a neuron to neuron that has a very tight junction with no real synaptic cleft, but more like a gap junction. And this is a bridge between the two neurons. So again, uncommon. We're not really going to talk much about it. Moving on to chemical synapses, we have a lot of chemical synapses. So what we mainly talk about with this are neurotransmitters. And the neurotransmitter is a chemical. We abbreviate neurotransmitter as NT. You guys already learned about one neurotransmitter, which was acetylcholine, right? So neurotransmitters are chemical, and that's why it says a neurotransmitter opens or closes an ion gate to the channel. So this is just like the neuromuscular junction between the neuron and the skeletal muscle. So events of an impulse transmission at a synapse. These are action potential reaches the axon terminal. Okay, so I have synaptic knob. So some of your notes might say axon terminal, synaptic knob. There's another word I was trying to think of. Anybody remember? No. The end of the terminal, the end, the knob, all saying the same thing. So reaching the synaptic knob, because remember, it's all or none, and it's going to go the whole length anyway, so it's going to go all the way down there. Oh, axon ending, that's what I meant to say. Synaptic knob, axon ending, axon terminal. So again, that meant that you had a 100 millivolt change, right? You went from negative 70 to a positive 30 millivolts. This causes calcium gates to open. Okay, so just like in the sarcoplasmic reticulum, a voltage change opened the calcium gates. High amount of calcium in one area would flow to the low amount of calcium in the other, just like regular diffusion, right? So that's why the calcium will flood in. So the vesicles fuse with the membrane. The neurotransmitter then is released into the synaptic cleft. So the calcium is what helps the vesicles fuse to the membrane and allow then the acetylcholine, if you're going to use that as your neurotransmitter, to be released from the presynaptic axonal terminal into that synaptic cleft, just like it did with the muscle cell. We briefly said how sodium would come in and cause calcium, but we didn't talk a whole lot about it because we're going to talk more about it in neurophysiology. So vesicles fuse with the membrane, neurotransmitter is released in the synaptic cleft. That was kind of like the acetylcholine. And neurotransmitter diffuses across the cleft and binds to sodium gates on the postsynaptic neuron. So on the skeletal muscle, it fused with the motor end plate, which then opened the sodium gates. In this case, they're actually touching the sodium gates, and that's what opens the gate to allow sodium then to come into the postsynaptic neuron soma or dendritic end. Okay, so postsynaptic sodium gates open and the cell begins to depolarize. So if it's small little things, it'd be graded potentials. If you get enough graded potentials, you'll get an action potential if you hit negative 55. Okay, so then it says postsynaptic potentials or PSPs occur at the postsynaptic neuron. That's why it's called PSP, and these are graded potentials. Lots of little ones until you get your actual, right? Okay, so on this beautiful, lovely picture that you can hardly see, if you really want to see it in your e-text or in your textbook, it's figure 12.15. And what it's talking about here is whether you get an EPSP or an IPSP. So you'll get familiar with these terms in just a moment. So -70, which is right here, and this line right there is your resting membrane potential. And you have the same in this picture right here. There's your resting membrane potential at -70 millivolts, okay? Threshold, we said, is what? -55 millivolts. So that's what this area here is on both pictures, -55. Now, if you can have your resting membrane potential and use graded potentials that would bring it closer to threshold, okay? So let's say instead of -70, you make it -68 or -63, somewhere in there. That's the little blip that you're seeing right here, okay? It's causing, is it bringing it closer to threshold or further away from threshold in the first picture? It's bringing you closer to threshold. In the second picture, notice it's dipping away. It's becoming more negative. So instead of -70 at your resting membrane potential, maybe you're at -72 or -75. So is it bringing you closer or further away from threshold? Further away. So it's going to take more to get to threshold. So if you're getting closer to threshold, it means you don't need as much, right? And if you're further from threshold, it means you're going to need more to get to it, okay? So an EPSP, or an excitatory postsynaptic potential, okay, is bringing you closer to threshold typically. These are graded potentials that bring you closer to threshold. They're called an EPSP, or excitatory postsynaptic potential. SP, yes. If you're going further from threshold, it's going to be called an IPSP, or inhibitory postsynaptic potential. Because what it's saying is you're either exciting it and getting it closer to the other cell getting to fire, or you're getting further away from it, you're inhibiting it from getting ready to fire, essentially. So an EPSP is going to be more like a depolarization, and you need enough to get to threshold. An IPSP would be more like a hyperpolarization, right? Because it took you further away and it's going to take more to hit threshold. So EPSP, or excitatory, is neurotransmitter binding, causes depolarizations that bring you closer to threshold. It doesn't necessarily mean you will get to threshold, though. It just depends on the number of graded potentials you get that would finally get you there. And an IPSP might bring you further away, but it just depends. And what happens is you actually have to add the two together to see, because you could actually have multiple neurons giving different signals to one neuron itself. So we'll talk about that in a second. But a synaptic integration means a single EPSP cannot trigger an action potential. You're going to need many graded potentials, or EPSPs, to finally trigger that action potential. So this is that idea of summation by a postsynaptic neuron. This is your EPSPs plus your IPSPs, I'll put a little S so that you know it's multiple ones, are added together at the axon hillock, and you're hoping to reach threshold and if you do, then the axon will fire, which means you definitely get an action potential if it adds up enough to get to threshold. So remember, you are adding positive and negative numbers here, because inhibitory is going to make you more negative. And if you can still overcome that, you will still, if you hit threshold, then you will get your action potential. So it says temporal summation means one neuron rapid fire. So it's one neuron is dumping neurotransmitter, and it might be like acetylcholine, and it might be like +5 amount. And it might do a little bit more, another positive 5 amount, and another positive 5 amount. And if it gets 3 of those, let's say, right, because that'd be 5, 5, 5 is 15, then you'll hit threshold, yes? Yes, okay. If you have spatial summation, that means many neurons are firing at the same time. So if you have many neurons firing at the same time, it just depends how many. You could have one neuron that gives you a positive 5 millivolt amount. Another one could give you a positive 10 millivolt amount. And if you have a 10 and a 5 and you get positive 15, you will hit threshold, even though 2 different neurons stimulated the neuron that needs to fire. Does that make sense? Okay. Or you could have 3 that are 5, 5, and 5. So temporal means it's one neuron that does it all. Spatial means you have a couple different ones that are doing it. Axon-hillock means you have to keep track of the potentials reaching the axonal area. So this means you're counting up the IPSPs and EPSPs. You need 15 millivolts, positive 15 millivolts, in order to hit your threshold. Okay, and that would automatically generate your action potential. So I'm going to diagram the summation, but we're out of time. So you guys can try to do maybe a picture of your own. When we come back, I will actually draw out the pictures and we'll talk about the synaptic integration and how that looks, and then we'll move on to neurotransmitters on the next class. And for those of you here, you now get your clickers.